Welcome to Science Aura. I am your host, Dr. Sachi Vale. We live in an era where data is the most valuable currency, but what happens when the mathematical foundations protecting our global military secrets are on the verge of collapse? Today, we dive deep into the dawn of a new security epoch: quantum cryptography. This is not just an upgrade to our current firewalls. It is a fundamental shift that relies on the immutable laws of physics rather than solvable mathematical puzzles. For decades, military forces worldwide have relied on complex algorithms to encrypt sensitive communications. These systems work because classical computers would take thousands of years to crack the mathematical key, but the horizon of technology is shifting rapidly. The advent of powerful supercomputers and the looming shadow of functional quantum computing mean that these mathematical fortresses are no longer impenetrable. A new paradigm of absolute security is desperately required. To understand the magnitude of this shift, we must first look at how classical encryption operates. Imagine a highly secure vault locked by a mathematical problem so complex that it baffles the greatest minds. Current encryption standards, like the Advanced Encryption Standard, or RSA, rely on the difficulty of factoring massive prime numbers. It is a one-way street, easy to multiply two primes together to create a key, but incredibly difficult to reverse engineer that multiplication. This mathematical asymmetry has been the bedrock of digital security, safeguarding everything from your personal banking details to classified military strike coordinates. However, this security is entirely conditional. It assumes that the adversary lacks the computational power to perform brute force calculations within a meaningful time frame. But what if that assumption is suddenly rendered obsolete by a revolutionary leap in computing hardware? This is where the quantum threat emerges. Enter the quantum computer. Unlike classical machines that process information in binary bits of zeros and ones, quantum computers use quantum bits, or qubits. These qubits can exist in multiple states simultaneously, thanks to a phenomenon known as superposition. This allows quantum computers to process vast amounts of possibilities concurrently, turning problems that would take millennia to solve into tasks that can be completed in mere seconds. The encryption shield is shattering. In the 1990s, mathematician Peter Shor developed an algorithm that theoretically proved a quantum computer could factorize large prime numbers exponentially faster than any classical machine. Shor's algorithm was a wake-up call to the intelligence community. It meant that the mathematical locks guarding our most critical infrastructure had a definitive expiration date. When a sufficiently powerful quantum computer is built, all current encrypted data becomes an open book to adversaries. This looming vulnerability has triggered a frantic global race. Intelligence agencies are already engaging in a practice known as store now, decrypt later. They are harvesting massive amounts of encrypted military intelligence, diplomatic cables, and strategic plans, hoarding them in vast data centers. They know they cannot read this data today, but they are patiently waiting for the day when quantum computing reaches maturity, allowing them to unlock these historical secrets with ease. The implications for national security are staggering. Imagine a scenario where submarine patrol routes, stealth aircraft telemetry, and underground missile silo launch codes are suddenly A compromised communication network in a combat scenario could lead to catastrophic strategic failures. To counter this existential threat, scientists and engineers realized they needed to abandon mathematics as the ultimate arbiter of security and turn instead to the fundamental laws of nature. This realization birthed the field of quantum cryptography, specifically quantum key distribution, or QKD. Instead of relying on human-made algorithms that can be cracked by smarter machines, QKD leverages the bizarre and unalterable rules of quantum mechanics. As Dr. Sachi Vale, I find this transition absolutely fascinating. We are moving from a paradigm of computational complexity to one of physical impossibility. You cannot cheat the universe, and quantum cryptography proves it. At the heart of this new security paradigm is the photon, the fundamental particle of light. Photons are incredible carriers of information. They travel at the speed of light, can be easily transmitted through fiber optic cables or the vacuum of space, and most importantly, they exhibit distinct quantum properties. By manipulating these properties, specifically their polarization, we can encode digital information directly onto individual particles of light, creating an unbreakable key. Polarization refers to the orientation of the electromagnetic waves that make up a photon. Imagine a photon oscillating vertically, horizontally, or diagonally. By assigning binary values to these different states of polarization, we can create a sequence of random ones and zeros. This sequence becomes the cryptographic key used to lock and unlock the actual message. But the true magic of quantum cryptography lies not in the encoding itself, but in how these photons behave when observed. To understand this, we must delve into one of the most famous principles of quantum mechanics, the Heisenberg Uncertainty Principle. Formulated by Werner Heisenberg, this principle dictates that certain pairs of physical properties, like position and momentum, cannot be simultaneously measured with absolute precision. In the context of quantum cryptography, it means that the very act of measuring a quantum system inevitably disturbs it. Observation is not a passive act in the quantum realm. When a sender, let us call them Alice, transmits a sequence of polarized photons to a receiver, Bob, they are establishing a secure key. If an eavesdropper, traditionally named Eve, attempts to intercept and measure these photons while they are in transit, she cannot do so without altering their quantum state. Eve is forced to guess the correct basis to measure the photon's polarization. If she guesses wrong, she irrevocably changes the photon, introducing an anomaly into the system. This leads us to another crucial rule of quantum mechanics, the no-cloning theorem. This theorem states that it is physically impossible to create an identical copy of an arbitrary unknown quantum state. Therefore, Eve cannot simply intercept the photon, make a perfect copy for herself, and send the original along to Bob. Any attempt to replicate the photon will fail, and the disturbance she caused during her initial measurement cannot be erased or hidden from the legitimate users. When Bob receives the photons, he and Alice compare a subset of their measurements over a public, unsecured channel. They are not sharing the key itself, but rather checking for errors. In a perfect, uncompromised transmission, their measurements will align perfectly according to the laws of probability. However, if Eve has been eavesdropping, the disturbances she caused will manifest as a high error rate in Alice and Bob's comparison. The intrusion is instantly and mathematically obvious. The beauty of quantum key distribution is its absolute transparency regarding security breaches. If the error rate exceeds a certain threshold, Alice and Bob know definitively that the channel is compromised. They simply discard the compromised key and try again. The actual secret message is never transmitted until a completely secure, unintercepted key has been successfully established. It is a self-destruct mechanism for information, triggered by the mere gaze of an unauthorized party. This level of security is unprecedented. It means that no matter how powerful a supercomputer an adversary possesses, no matter what mathematical algorithms they develop in the future, they cannot break a quantum key without violating the fundamental laws of physics. Quantum cryptography provides what is known as information theoretic security. It is mathematically proven to be unbreakable, offering a permanent shield against the encroaching threat of quantum computing decryption capabilities. Now, let us move from the theoretical realm of quantum physics to the practical realities of military deployment. How do we build this unbreakable network? The foundation lies beneath our feet, in vast, subterranean networks of fiber-optic cables. These cables, made of ultra-pure glass, are the highways for our quantum-encoded photons. Military installations are increasingly relying on these dedicated underground lines to establish secure communication channels immune to surface disruption. The underground environment provides a stable, controlled medium for delicate quantum transmissions. Unlike radio waves or microwave communications, which can be affected by atmospheric conditions, solar flares, or deliberate electronic jamming, fiber optic cables offer a shielded conduit. Photons traveling through these subterranean glass fibers are protected from electromagnetic interference, ensuring that the fragile quantum states remain intact over significant geographical distances. In the theater of modern warfare, electronic warfare, or EW, is a critical component. Adversaries deploy advanced jamming devices designed to saturate communication frequencies with noise, blinding radar systems, and severing command and control links. Classical wireless communications are highly susceptible to these tactics. However, a quantum network operating through underground fiber optic cables is virtually immune to such electronic suppression. You cannot jam a photon traveling in a buried pipe. Let us dive deeper into the mechanics of this process, specifically the BB84 protocol, the first quantum cryptography protocol developed in 1984. Imagine Alice has two sets of polarization filters. A rectilinear set, which polarizes light vertically or horizontally, and a diagonal set, which polarizes light at 45 and 135 degree angles. For each bit of data she wants to send, she randomly chooses one of these filters to encode the photon before transmitting it. Bob, on the receiving end, also has these two sets of filters. Because he does not know which filter Alice used for any given photon, he must guess. He randomly selects either the rectilinear or diagonal filter to measure the incoming photon. If he guesses correctly, he measures the exact state Alice sent. If he guesses incorrectly, the Heisenberg Uncertainty Principle dictates that his measurement will yield a random result, destroying the original information encoded in that photon. After all photons are sent, Alice and Bob communicate over a public channel. They do not reveal the actual polarization states, but only the sequence of filters they used. They discard all instances where Bob guessed the wrong filter. The remaining instances, where their filter choices matched, form the basis of their shared secret key. This process, known as sifting, distills the raw transmission down to a perfectly correlated sequence of bits, known only to the sender and the receiver. But what if Eve was listening? If Eve intercepts the photons, she must also guess which filter to use for measurement. Since she does not know Alice's choices, she will guess wrong about half the time. When she resends the photons to Bob, she inadvertently sends them in the wrong state. Even if Bob guesses the correct filter to match Alice, the photon he receives has been altered by Eve. This introduces a measurable error rate into the sifted key, acting as an unavoidable tripwire. In classical systems, errors can be attributed to line noise or faulty equipment. In quantum systems, while some natural noise exists, any error rate above a specific threshold is mathematically guaranteed to be the result of eavesdropping. If Alice and Bob detect an error rate exceeding roughly 11%, they know Eve is present. They immediately abort the protocol, discard the compromised key, and begin the transmission anew. The secret message is never placed at any risk. If the error rate is below the threshold, Alice and Bob proceed to the next critical phases: error correction and privacy amplification. Error correction involves using classical algorithms to locate and eliminate the small number of errors caused by natural channel noise, ensuring both parties possess identical keys. Privacy amplification goes a step further, mathematically shrinking the key to exponentially reduce any partial information that Eve might have managed to glean during transit. The result is a symmetrical cryptographic key that is theoretically perfectly secure. This key can then be used in conjunction with a one-time pad encryption algorithm. The one-time pad is the only classical encryption method mathematically proven to be unbreakable, provided the key is truly random, as long as the message itself is never reused and is kept completely secret. Quantum key distribution solves the exact problem of securely distributing that perfect, unbreakable key. Beyond the BB-84 protocol, there is an even more profound quantum phenomenon being harnessed for military security: quantum entanglement. Albert Einstein famously referred to it as spooky action at a distance. When two particles become entangled, their quantum states are inextricably linked, regardless of the physical distance separating them. Measuring the state of one entangled photon instantly determines the state of its partner, even if they are situated on opposite sides of the planet. This bizarre property forms the basis of entanglement-based protocols, like the E91 protocol developed by Arthur Eckert. In this system, an independent source generates pairs of entangled photons, sending one to Alice and the other to Bob. Because their states are correlated, Alice and Bob can perform measurements on their respective photons to generate a shared key. The beauty of this approach is that they do not even need to trust the source generating the entangled photon pairs. If an eavesdropper attempts to intercept one of the entangled photons, they destroy the delicate entanglement. This disruption is immediately detectable by Alice and Bob when they analyze the statistical correlations of their measurements using Bell's inequality test. Entanglement-based cryptography offers an even stronger security guarantee, moving the trust away from the physical hardware and placing it entirely within the mathematical verification of the entangled quantum states themselves. However, practical implementation of quantum cryptography faces significant physical hurdles. The most pressing challenge is distance. Photons traveling through fiber-optic cables are subject to attenuation. Over long distances, the glass absorbs some of the light, causing the signal to degrade and eventually vanish. Currently, a standard quantum key distribution link over commercial fiber optics is limited to roughly 100 to 200 kilometers before the signal becomes too weak. In classical networks, this signal loss is mitigated by using optical amplifiers, which boost the signal at regular intervals. But remember the no-cloning theorem? We cannot simply amplify or copy a quantum signal without destroying the delicate quantum information it carries. If we try to boost the photon, we alter its state, rendering the cryptographic key useless. Therefore, securing a vast continent-spanning military network requires a radically different technological approach. The theoretical solution to this distance limitation is the quantum repeater. Unlike classical amplifiers, a quantum repeater does not copy the signal. Instead, it relies on the phenomenon of entanglement swapping. Imagine dividing a long distance into several shorter segments. The repeater generates entanglement between the endpoints of these smaller segments, and then mathematically links them together, effectively stretching the entangled state across the entire distance of the network. Developing fully functional quantum repeaters is currently one of the most intense areas of research in quantum physics. It requires the ability to store quantum information in specialized quantum memories for brief periods, while the entanglement swapping operations are performed. These quantum memories often utilize ultra-cold atoms or specialized crystalline structures to trap and preserve the fragile photon states, a feat of engineering that pushes the boundaries of modern material science. While ground-based quantum repeaters are still in the experimental phase, military strategists cannot afford to wait. The immediate solution to the distance problem has been to look upward toward the vacuum of space. The atmosphere absorbs photons, but the vast emptiness of space does not. By placing quantum communication nodes on satellites orbiting the Earth, we can bypass the attenuation limitations of terrestrial fiber optic cables and establish global quantum security links. In 2016, a monumental milestone was achieved with the launch of Micius, the world's first quantum science satellite. Orbiting at an altitude of 500 kilometers, Micius demonstrated the ability to generate entangled photon pairs in space and beam them down to ground stations separated by over 1,200 kilometers. This experiment proved that space-based quantum key distribution was not just a theoretical concept, but a viable architecture for global communication. The military implications of quantum satellites are profound. A constellation of these satellites could create a global, unhackable command and control network. Submarines operating in deep waters, stealth bombers flying over hostile territory, and forward deployed military units could all receive unbreakable cryptographic keys directly from space. This eliminates the reliance on vulnerable terrestrial infrastructure and ensures secure communications in any theater of global operation. However, space-based quantum communication is not without its own set of extreme challenges. Beaming a single photon from a satellite moving at incredibly high speeds to a small telescope on the ground requires unprecedented precision. It is akin to hitting a moving coin with a laser pointer from hundreds of miles away. Atmospheric turbulence, cloud cover, and even background light from cities can disrupt the fragile quantum signal, requiring sophisticated adaptive optics to maintain the link. To overcome these atmospheric disturbances, military research is focusing on developing hybrid networks. These networks combine the global reach of quantum satellites with the reliability of underground fiber-optic grids. Satellites act as trusted nodes, beaming quantum keys to highly secure, heavily fortified ground stations. These ground stations then distribute the keys through the subterranean fiber-optic networks to military bases, missile silos, and strategic command centers. Let us examine the strategic value of securing underground missile silos with quantum cryptography. These silos house the ultimate deterrence of a nation's nuclear arsenal. The communication lines connecting these silos to national command authorities must be absolute and infallible. Any possibility of an adversary intercepting, altering, or spoofing launch commands could lead to an accidental nuclear exchange or the neutralization of a nation's second strike defense capabilities. Classical encryption, vulnerable to future quantum computer attacks, is deemed insufficient for securing these apocalyptic assets. By integrating quantum key distribution into the subterranean cables linking these silos, military commanders ensure that launch orders are authenticated by the laws of physics. If an adversary attempts to tap into the underground cables, the quantum state collapses, the error rate spikes, and the system automatically locks down, preventing any unauthorized access. This level of automated, physics-based intrusion detection is a game changer for strategic defense. It shifts the defensive posture from reactive to proactive. In traditional cybersecurity, an intrusion might go unnoticed for months, allowing adversaries to silently exfiltrate data or plant malicious code. In a quantum-secured network, the intrusion is detected instantaneously at the fundamental particle level. The alarm is triggered the moment the unauthorized observation occurs. Furthermore, quantum cryptography offers a robust defense against the rising threat of harvest now, decrypt later strategies. As mentioned earlier, adversaries are stockpiling encrypted data today in anticipation of tomorrow's quantum computers. But data encrypted with keys generated by quantum key distribution is immune to this tactic. Because the key exchange itself is mathematically proven to be secure against any future computational advancements, the stored data remains permanently locked. The transition to a quantum-secure military infrastructure is an immense logistical and financial undertaking. It requires replacing or retrofitting existing communication hardware with specialized quantum transmitters and receivers. It necessitates the laying of dedicated, ultra-pure fiber optic cables and the deployment of new constellations of quantum satellites. It is a fundamental overhaul of the global military nervous system. Driven by the absolute necessity of maintaining strategic superiority This technological arms race is not limited to just encryption. The development of quantum computers, the very machines that threaten classical cryptography, is also a top military priority. Quantum computers promise to revolutionize logistics, accelerate the discovery of new advanced materials for armor and weaponry, and optimize complex battlefield strategies in real time. The nation that achieves quantum supremacy will hold a decisive advantage across all domains of modern warfare. However, the immediate focus remains on defense. The concept of quantum resilience is becoming a central tenet of national security doctrines. Quantum resilience means building systems that can withstand attacks not just from today's supercomputers, but from the theoretical quantum computers of the next decade. It is about future-proofing the military's most critical data against an adversary whose technological capabilities are evolving at an exponential and unpredictable rate. Consider the vulnerability of the Global Positioning System, or GPS. Military operations rely heavily on GPS for navigation, targeting, and timing synchronization. However, GPS signals are relatively weak and susceptible to spoofing or jamming. Adversaries can broadcast false GPS coordinates, leading drones or missiles astray. Quantum technologies offer a solution here as well, through the development of quantum sensors and highly precise quantum clocks that operate independently of satellites. Quantum clocks utilize the ultra-stable oscillations of atoms to measure time with unimaginable precision. By integrating these clocks into military vehicles and command centers, forces can maintain precise synchronization even if GPS signals are jammed or compromised. This ensures that encrypted communication networks, which often rely on strict timing protocols, remain functional in highly contested electronic warfare environments. Further solidifying the resilience of the quantum infrastructure. The integration of quantum cryptography into naval operations presents unique challenges. Submarines, the ultimate stealth platforms, cannot trail fiber-optic cables, and highly conductive seawater heavily attenuates electromagnetic signals, including light. Communicating securely with submerged vessels currently relies on extremely low-frequency radio waves, which have very low bandwidth and are not suitable for complex cryptographic key exchange. Quantum technology must adapt to this harsh domain. Researchers are exploring the use of blue-green lasers for underwater quantum communication. Water is relatively transparent to these specific wavelengths of light. By beaming polarized photons using blue-green lasers from aircraft or satellites to receivers on submarines, it might be possible to establish secure quantum links beneath the waves. While still highly experimental, overcoming the scattering and absorption of photons in the ocean is a critical objective for naval strategic security. As we push the boundaries of quantum mechanics, we are also exploring the concept of device-independent quantum key distribution. In standard QKD, there is an underlying assumption that the physical equipment, the lasers and detectors, are functioning exactly as intended and have not been tampered with by a sophisticated adversary. If the hardware itself is compromised, perhaps through a supply chain attack, the theoretical security guarantees of the quantum protocols could be undermined. Device-independent protocols seek to eliminate this vulnerability. By relying on complex statistical tests of quantum entanglement, specifically Bell's theorem violations, these protocols can verify the security of the key exchange even if the devices themselves are untrusted or potentially malicious. The security is derived entirely from the observed correlations between the measurement outcomes, completely independent of the internal workings of the black box hardware generating the photons. This represents the pinnacle of cryptographic paranoia and security. It ensures that even if an adversary manufactured the very communication equipment the military is using, they still could not intercept the keys without being immediately detected. Device-independent quantum cryptography is incredibly challenging to implement, practically due to the stringent requirements on detector efficiency and channel loss, but it represents the ultimate holy grail of unhackable military communication systems. The geopolitical implications of this quantum leap are profound. We are witnessing the dawn of a new Cold War, one fought not with nuclear warheads, but with qubits and entangled photons. Nations are investing billions of dollars into national quantum initiatives, racing to build the first comprehensive quantum communication networks. The ability to guarantee absolute secrecy while simultaneously possessing the computational power to break an adversary's classical encryption is a paradigm-shifting advantage. This advantage could destabilize the current global balance of power. If one nation achieves a mature quantum decryption capability before others have transitioned to quantum secure networks, they could theoretically access decades of classified intelligence and compromise real-time strategic communication. This window of vulnerability is driving the urgent accelerated deployment of quantum key distribution networks across allied military alliances to ensure collective security in the quantum age. The architecture of these future military networks will be fundamentally different. We will see the rise of quantum key infrastructures, parallel networks dedicated solely to the generation and distribution of cryptographic material. These infrastructures will act as the secure foundation upon which classical data networks operate. The data itself may still be transmitted over standard encrypted channels, but the keys unlocking that data will be continuously refreshed via the unhackable quantum links. This continuous key refreshment is crucial. In classical systems, a single cryptographic key might be used for hours or even days to encrypt large volumes of data. If that key is eventually compromised, all data encrypted during that period is exposed. Quantum key distribution allows for the rapid, continuous generation of new keys, potentially refreshing the encryption several times a second. Even if one key were somehow compromised, the exposure is limited to a mere fraction of a second of data. Managing this vast influx of cryptographic keys requires highly automated, intelligent network management systems. Artificial intelligence and machine learning algorithms will play a vital role in routing quantum keys across complex, dynamic topologies, optimizing the performance of the quantum network in real time. These AI systems will monitor error rates, detect potential intrusion attempts, and automatically reroute quantum links to bypass compromised or degraded nodes within the military infrastructure. The synthesis of artificial intelligence and quantum cryptography creates a self-healing, immensely resilient defense network. It is a system that not only detects attacks with absolute physical certainty, but also dynamically adapts to maintain secure connectivity. This is the future of command and control. A network that is mathematically unhackable, physically tamper-evident, and intelligently adaptive to the chaotic and unpredictable conditions of modern high-tech electronic warfare environment. Let us return to the physical infrastructure, specifically the critical role of the optical fiber itself. Not all glass is created equal. The fibers used in quantum communication must be of the highest optical purity to minimize photon absorption. Furthermore, they are highly sensitive to environmental changes. Variations in temperature or mechanical stress on the buried cables can alter the polarization state of the photons, introducing errors that mimic the presence of an eavesdropper. To mitigate this, military engineers employ active stabilization techniques. Sophisticated monitoring equipment constantly measures the environmental conditions along the fiber-optic routes and applies real-time corrections to the polarization of the transmitted photons. This ensures that the delicate quantum states remain stable even as the ground above the cables shifts or temperatures fluctuate. It is a continuous, high-precision balancing act required to maintain the integrity of the quantum link. Furthermore, the physical security of the ground stations and repeater nodes is paramount. While the quantum link itself is secure against interception, the endpoints where the photons are generated and detected are vulnerable to conventional attacks. These facilities must be heavily fortified, often located deep underground, within hardened military bunkers, protected by multiple layers of physical security, biometric access controls, and strict electromagnetic shielding to prevent side-channel data leak. A side-channel attack does not target the quantum encryption directly, but rather exploits vulnerabilities in the physical implementation of the hardware. For example, an adversary might attempt to measure the power consumption of the laser diode generating the photons or analyze the electromagnetic emissions from the single photon detectors. By carefully analyzing these physical emanations, and they might deduce information about the cryptographic key without ever interacting with the photons themselves. Defending against side-channel attacks requires rigorous engineering and meticulous hardware design. Equipment is enclosed in Faraday cages to block electromagnetic radiation, power supplies are heavily filtered to obscure energy consumption patterns, and the optical components are carefully isolated to prevent any unintentional leakage of information. The security of a quantum network is only as strong as its weakest link, and ensuring the absolute integrity of the endpoint hardware is a continuous challenge. Looking ahead, the ultimate vision for military security is the quantum internet. This is not just a network for distributing cryptographic keys, but a fully integrated global system capable of transmitting actual quantum information between quantum computers. A quantum internet would allow for distributed quantum computing, where multiple quantum processors across the globe collaborate on complex simulations,